Hello everyone, my name is Fangyan Lao. I'm a research scientist in the School of Mechanical Engineering at Purdue University. My research aims to reduce emissions as well as enhance the safe operation of gas turbine engines in both aviation and land-based power production applications. Today, I will introduce the technology for compressor stall warning in gas turbine engines. Gas turbine engines serving as power plants are often likened to the heart of airplanes and ships. Using the same logic, compressor stall is like a type of heart attack to gas turbine engines. So when compressor stalls, it can cause severe damages to the engines. Besides, like heart attacks to human beings, compressor stall can occur without apparent precursors. So the key challenge in gas turbine engines for stall warning is to identify the small disturbances associated with stall from the ones related to turbulent flows inside the engines. Here is an example of the consequence of compressor stall in gas turbine engines. The right figure shows one engine of a Boeing 777 caught on fire during takeoff when the compressor stalls unexpectedly. Um, Another fact here is from 2008-2012, only in the aviation sector, 4 turbofan engine failures were reported due to the compressor stall, and they result in losses of more than $50 million. Therefore, an effective stall warning and avoidance technique is of great value to the industry. At Purdue University, we jump out of the box and approach the problem differently. We developed an ECG for gas turbine engines to monitor the engine's rhymes and warn potential heart attacks in gas turbine engines. As shown in the right figure, the rhymes in gas turbine engines were monitored using a single or multiple fast response transducers placed at appropriate locations. In normal operations, harmonic rhymes were expected, while before compressor stalls, the small stall precursors are caught using a nonlinear feature extraction algorithms and provides a warning to the engines. This technology has been applied to 2 different compressors in a laboratory environment with success, and the technology reaches to a TRL of 4. Comparing to other competing techniques, this technique offers higher accuracy, longer warning time, and is also more robust. And besides, it offers flexible marketing strategies. The technique can be easier developed to a standalone product marketing towards the end users of gas turbine engines, or be integrated into the state-of-the-art engine health monitoring system with marketing towards gas turbine engine OEMs. And currently, we are looking for both industrial partners as well as investors to mature this technology for its application in gas turbine engines. That's everything I have for today. Thank you for your time.
As I mentioned during my introduction, I'm here on behalf of the Technology Transfer Office at NSWC Crane to talk to you about unique inventions that are coming out of our labs, like this one, the Hybrid Photonic Receive Antenna. This is an ongoing effort by Kevin Keller, a senior research and development engineer with over 20 years of federal lab experience, as well as private industry experience and experience as an entrepreneur. He's very interested in transitioning this technology from the federal labs to the private industry. The problem Kevin was and is investigating was a novel approach to mitigating beam squint in antennas. Beam squint refers to the change in the beam direction as a function of operating frequency, polarization, or orientation, and is important because it can limit the bandwidth in phased array antenna systems. Phased array antenna systems are used widely and in many different industries. For Crane, these antenna systems are directly applicable to unmanned systems such as UAVs and drones or ground vehicles. There are many applications outside of the military as well, such as communications, satellites, weather research, meteorology, and optics. However, after many years, much research, and many millions of dollars trying to mitigate beam squint, it's still a concern in the phased array antenna industry. Kevin's work is a revolutionary concept and a new way to mitigate beam squint. Kevin's initial concept recognized that the electric field which develops across a patch antenna is very similar to the electrical field which is used to develop the phase delay in an optical phase modulator. The challenge was to find a material that would provide both the dielectric and the electro-optic coefficients required. To date, he has developed antenna architecture that uses optical phase delay as the primary means of gathering information instead of traditional electrical signals. His designs are a significant improvement over the conventional phased array antennas. From the chart below, you can see some of these advantages such as smaller footprint, lighter weight, no copper wires or shielding, improved aerodynamics, better performance through less signal loss. To this date, Kevin has been able to partner with another institution to help prototype his wafers. However, he is still interested and searching for partners in both industry and academia to help with fabrication, and he's also specifically looking for a collaboration partner with experience in high coefficient EO polymers. The intellectual property for this has been filed and the patent has issued and is available for licensing. If you are interested in this technology, a licensing opportunity, or perhaps a partnership with Kevin himself, please reach out to myself or to the Technology Transfer Office at NSWC Crane. Thank you very much.
Hello everyone, and welcome to my talk on the piezoelectric sensor for concrete strength monitoring. I'm Luna Lu, a professor from Purdue University. Our technology addresses the big issue in the construction industry, which is lack of the reliable sensing methods to determine real-time strength of the concrete structure. And therefore, there's no data-driven decision to optimize the construction schedule, which often ended up for problems. For instance, after major highway renovation, you could open the traffic earlier, but then that's often caused premature damage failure. And you ended up fix the highway or construction infrastructure for every 6 months, or you could delay the traffic opening time, and that will increase the cost, increase the time, and also leads to a traffic congestion. And current industry practice is to use the cylinder testing. As we all know, the cylinder testing is highly dependent on the skills, how you fabricate a cylinder, how you cure the cylinder, and also it's very unreliable to correlate the strength of a very small cylinder, 4x6 cylinder, to 3 miles of the highway. So therefore, there is significantly increased false negative results due to the lower break of the cylinder. To compensate that lower negative results, the industry practice is to put excessive material, and to overcompensate that strength is typically about 10 to 15% of the cement, which is a significant waste of the material. In order to understand the market size, my research team has participated in the 2020 National Science Foundation Innovation Corps program and interviewed more than 120 potential customers in Department of the Transportation, construction company, insurance company, and many associated industries. So we have identified the primary market is in vertical construction for high-rise building because they are very schedule-driven, and the precast concrete plant. The secondary market can be horizontal construction, particular pavement, bridges, and insurance, large infrastructure company, and the dams. So the market size can be determined by 3 tiers. For 10, it's 1.5 billion. That's including concrete strength testing, labor, and equipment in the United States. Vertical construction is our SAM. That's about 859 million. And we would like to focus on real-time monitoring for vertical construction in the United States. That's about $500 million per year. I would like to emphasize this data is purely based on US information. Of course, the technology is applicable worldwide. To address this urgent and a big market need, our technology consists of two components. One is AI-guided algorithm for concrete strength measurement and prediction. By using this algorithm, we can accurately measure the concrete and also predict how the strength development, so the construction engineers can better schedule around that strength prediction. And secondly, we have developed a miniaturized hardware, including the sensors for data collection and also processing and computation system and the Wi-Fi transmission. Compared to the current market available technology, and the sensor we developed at Purdue has 5 major feature and benefits. One, it can directly measure mechanical data, and we do not need extensive calibration process, and we can provide a real-time monitoring, and this monitoring can be wirelessly. And currently, it's the plug and play device. Device is portable as well. In contrast, in the cylinder break testing and the beam testing, which is the current practice in the industry, they are very small sample, they are not reliable, and also they don't provide a real-time monitoring. You're trying to correlate a small sensor with large concrete structure, and definitely not portable. The hydraulic cylinders testing is very expensive, and only can be done in a lab. And on the other hand, you have a maturity testing. However, maturity testing require extensive calibration process. The reason because they measure the temperature data, they don't measure mechanical data. So you need to have that extensive calibration to correlate the temperature with the strength development. That typically takes 1 week, at least $3,000 to establish that curve. So what we are looking for, we're looking for excellent partners to help commercialize the technology and scale up the technology. We're looking at investor collaboration. We're looking at also the people who join the team. So if you're interested in the technology, please contact me at luna@purdue.edu. Thank you.
Hello everyone, my name is Howell Lee, and I'm going to talk through the traffic signal we call Go, Go, Go system. I would like to acknowledge my co-inventors, Tom Platty and Gijo Matthew. So the motivation for this invention is that every year, 2.5 million crashes occur at signalized intersections with 3,200 fatalities and hundreds of thousands of injuries. A quarter of those involve red light running. And as a side note, heavy vehicles like semis are twice as likely to run a red light. Example on the right is from a few years back, and the lady in her SUV was on her way to pick up her child from school and was hit by a semi running a red light. And because semis are 20 times heavier than your typical car or SUV, it's often very difficult when they see that yellow light, when they see the light change, to stop. Well, what can we do about it? Well, people will say, well, you can use smart traffic lights, but that idea has been floating around for a long time, not a lot of traction. And even the most advanced driver-assisted ADAS technologies and autonomous systems today cannot get this done. Some can tell you whether a light is green or red, but they can't change the status. And none of them can do that with the traffic signals we have out there today. These traffic signals make those decisions at a split second. There are 360,000 traffic signals in the country, and each signal requires about $20,000 in instrumentation, $10 billion total, to figure out whether the car's there or not. They can't talk to the car. I mean, to do that, and you got to run the wires, sensors, and the cameras all the old-fashioned way, right? Very expensive, very time-consuming, and you need maintenance on that. On top of that, the connected autonomous vehicle market is projected to be $48 billion in the next 6 years. And every year, there's still $65 billion in property damage, injury and the loss of life due to the crashes. So here's our technology. It consists of a radio at the signal pole and a radio on the vehicle. There's a thing called the traffic signal cabinet. There are aluminum boxes you can see on the side of the road that controls the timing, right? So we put intelligence in there to decode and process the signals. And depending on what the vehicle is doing, it changes the state of the light to operate more safely. So in this case, there's going to be a dilemma. Vehicle's heading towards the light. It's green now, but it's going to turn yellow when they get to that part of the street where they're not going to be able to stop. So should they stop or should they go? Our intelligence knows this. And what it does, sees the vehicle coming, extend the green so it can safely clear the intersection. Scenario 2, there's a car on the side street waiting, and we know that we can't extend it anymore because the guy's been waiting there for a long time, so he's got to go. So what do? Well, the dump truck's going to head towards that yellow zone. We don't want that dump truck to get that signal right before it turns yellow. We basically shift that yellow time early so that either the driver or any autonomous agent in the truck in the future can say, hey, I got to slow down because you're going to have to stop anyway. Why not slow down earlier so it's safer, right? So you get they get the message, comes to a safe stop, side street gets to go, no problems there. This is a video showing the prototype in the field that's just outside of Purdue with a passenger vehicle getting the early yellow indication. You can see the side streets having queued vehicles waiting to go. And our test vehicle gets that indication at 1,000 feet. We can set that any way we want at a safe distance, depending on the intersection. And compared to other technologies like conventional sensors, in-vehicle green light advisory or GLOSA, machine vision, AI, our system can do it all. Feature light status, extend green time, indicate yellow early, all without intrusive infrastructure like cutting loops. And here's my last slide. The technology has already been submitted as a non-provisional patent in August last year. We're looking for partners in the automotive, heavy vehicle, or OEM space. We estimate the startup capital to be $500,000 over 18 months for pre-seed. Our goal is to get 5 agencies installed, 2 intersections each. And with that, thanks for your time. Go, go, go.